Thank you very much to Harold for his nice words, and also thank you to the organizers, especially to Jose, for the opportunity to come here again to see my friends. And in my talk today, I would like to explain some results which are contained in a paper which is not, well, it was updated to the archive some months ago, but actually it's pretty old, but we have never explained that. So in order to, which is a joint work with Bill Mix, as you can see there from the University of Amherst, Massachusetts. And in order to motivate the problem I'm going to deal with, I'm going to start by, showing you two, actually three, but you will see the third one in a minute, theorems, pretty famous. And the first one is by Golding and Menicosi, published in the Annals, 2008. They proved that if you have, in R3, a complete embedded minimal surface, right, and assume it has finite topology, then the intrinsic, say, property of completeness transforms, implies the extrinsic one of properness, right? By analyzing the ideas in that paper, Bill and Harold were able to prove the minimal lamination closure theorem, right? That replace R3, but by a Riemannian three-manifold N3, and then there you suppose you have a complete embedded minimal surface, and now instead of assuming finite topology, assume positive injectivity radius, right? Then in general, maybe or maybe not, the surface could be proper, but if not, at least it has a very important property, is that the closure of that has a very nice structure. It's a minimal lamination, which means that maybe it's not just a surface, it's a collection of surfaces, but it has a local product structure, and you can analyze that structure, right? Actually, this is a generalization of the first theorem, because by using Gauss-Bonnet and also the one-sided curvature estimate of Golding-Menicosi, you can reprove theorem 1. So I'm going to skip that, because it's not relevant for my talk. And in the same paper, Bill and Harold prove another very nice theorem that you have there. If N3 is a product of a surface, Riemannian with a real line, and there you have a complete embedded minimal surface of finite topology, so we come back to the hypothesis in theorem 1, then also the closure has that structure. It's a minimal lamination, right? And at this point, I want to mention very nice work of Álvaro Kruger, which is here. He worked on more or less the same lines in his PhD in the last chapter, and, but when the ambient space being a hyperbolic manifold or a Hadamard manifold with certain conditions, right? So in my talk today, I would like to say some properties. What can we say in the case that instead having a product or a hyperbolic manifold, say, right, we have a homogeneous three manifold or a locally homogeneous one, right? So that's the goal of my talk, and this is the theorem. The theorem says that if in a complete locally homogeneous manifold, N3, you have a complete embedded minimal surface of finite topology, then first, the closure is a minimal lamination, right? That's what I'm going to call the main statement. And then also, if the ambient space has positive injectivity radius, then the surface has the same property. If the scalar curvature of the ambient manifold, which is constant, is a number because the ambient space is locally homogeneous, right? If that number is positive, then you recover properness. Then M has to be proper. More generally, if the scalar curvature is non-negative, but you also assume simply connectivity for the ambient space, then the surface has to be proper again. And finally, if you are in the compact case, so add to the hypothesis in 3, add the compactness for the ambient space, then you end up with S3 endowed with a life invariant metric, right? This is SU2. Then the surface has to be compact. Okay? So the remaining part of my talk is try to give an idea of how to prove this, right? And okay, first is that this is a remark that is contained in the minimal lamination closure theorem by Bill and Harold. is that instead of proving directly that the closure is a minimal lamination in the main statement, right, it suffices to show that the injectivity radius function, that's the meaning of IM, right? The injectivity radius function of the surface is bounded away from 0 in the intersection of the surface with any extrinsic ball, with the bound depending, of course, on the ball, right? So that's the meaning of Bn here. B will be ball in general. The sub-index refers to what is the distance that where you compute the ball. So this is the extrinsic ball. If you see Bm, that you will see later, then that is an intrinsic ball, right? Okay, so it suffices to show this. Second step is that because the surface has finite topology, then it has finitely many ends, and all of them are annuli topologically, right? So it suffices, because then the surface is built by a compact part, maybe with a lot of topology, but compact, right? And then finitely many annuli. And since, of course, the injectivity radius function is continuous, then it's positive in a compact part, and you only had to deal with the ends. So the only thing you had to show is that the injectivity radius function of the surface is bounded away from 0 in the intersection of any extrinsic ball with a given end, E, right, of the surface. Okay. So I'm going to assume for a moment, I'm going to assume that the main statement holds. So the closure is a minimal lamination. Why everything else holds? Well, actually, the same, I will prove later, or I will give a sketch of why M closure is a minimal lamination. So the same idea I'm going to show, I'm going to explain about the main statement, also shows that one holds, right? So I'm going now to concentrate on how to show, how to prove 2, 3, and 4, assuming the main statement, right? Right. So suppose I'm trying to prove item 2. Since I'm assuming that the closure is a minimal lamination, then the failure of being proper for the surface means that you can find a limit leaf in that lamination. That means that there is a leaf, it's a surface in that collection, in the lamination, which has a point. Actually, every point has the following property, is that that point is a limit of a sequence of points that either they belong to other, say, leaves of the lamination, or if they belong to the same leaf you started with, then that sequence converges in the ambient space, but it doesn't converge in the intrinsic topology. Right? That's the meaning of that. But by a theorem that Bill, Antonio Rosa, and myself proved some years ago, such a leaf has to be stable. Actually, the two-sided cover of that such a leaf has to be stable, right? But in my situation where the scalar curvature is positive, then there is a technique that I like to call Kawai's technique, but also Golding and Minicozzi use that technique. It's known this way also. Showed that in that situation, the only possible stable completeness is for free here, because it's a leaf of a lamination, are constant mean curvature surfaces are sphere or projective planes, right? So after passing to a two-sided cover in your situation, your, say, stable limit leaf will be a sphere. In particular, it will be compact. And then you have portions of your M converging to that compact thing, which of course implies that M disconnects into infinitely many components, which cannot be the case because I'm assuming from the beginning is connected, right? So that is a contradiction in that proves item 2. Regarding item 3, of course, I'm adding one more hypothesis, simply connected for the ambient space. So if I can assume that the scalar curvature is 0, right, by looking at 2, then if the scalar curvature is 0, there is a paper in the 70s by Milnor that says that the only possibilities there are R3, and then the theorem is theorem 1 by Golding-Minicozzi, right? or SU2, S3 with a left invariant metric. And then it suffices to show property 4, right? So I'm going to prove property 4. Huh? So instead of proving now that M is proper, we will prove M is compact, right? Property 4. So that is the statement I want to prove. So by contradiction, suppose M is not compact. Huh? I'm now living in SU2. Then because of the idea I said before, I'm assuming the closure has the structure of a minimal lamination. Because it's not proper, then it will have a limit leaf, and then the two-sided cover will be stable. Let's call L tilde to the two-sided cover of the limit leaf L, right? So in this hypothesis of a non-negative scalar curvature, stability implies, and completeness, implies that the surface has at most quadratic error growth, which in turn implies parabolic conformal structure. In this setting, parabolic conformal structure, we proved, means Magdalena Rodriguez and Jose Miguel Manzano, myself, we proved that space of bounded solutions, functions on the surface that satisfy the Jacobi equation, that linear space coincides with the space of Jacobi functions that have constant sign, either positive everywhere, negative everywhere, or zero, identically zero. And this is also a one-dimensional space, right? So how are we going to use this? So now think of, I'm in the ambient space of S3, so it's a Lie group. So now G, or this, I don't know, Gothic G, right, is, well, G is the left invariant, the set of left invariant vector fields. G star is the set of right invariant vector fields. Since I am in the ambient space of SU2 with a left invariant metric, every right invariant vector field is a Killing field, right? Then if you multiply a Killing field by the uninormal vector field of a minimal or constant mean curvature surface, automatically you produce a Jacobi function, right? Okay, so let us do this. Consider the uninormal vector field to L tilde, which is two-sided, so it has such a thing, and pick a point P in the surface, and pick two right invariant, linearly independent vector fields, which are defined not only in the surface, but everywhere in space, so that at the point P, they generate the tangent plane of the surface, right? And then compute the inner product of these Killing fields with the uninormal vector, right? This is a Jacobi function, and because you are in a compact ambient space, the vector field Fi has to be bounded, so then this is a bounded Jacobi function, right? And because of item 2, then the function has to have constant sign. But at the point P is 0, clearly, since F1 and F2 at P are tangent to the surface, right? So that means that UI, both are identically 0 along the surface L tilde, which means that the vector fields I took are everywhere tangent to the surface. And then because it's a surface, the Lie bracket along the surface has to be everywhere tangent again. But that's impossible because of the Lie group structure of SU2. If you have two linearly independent right invariant vector fields, the Lie bracket has to be in a direction which is generates with the other two the whole tangent space, right, to the ambient manifold. So that's impossible, right? Okay, so summarizing, what remains to show in the, or to explain in the talk is why if the main statement holds, which is that one again, right? I'm not going to read it again. So in order to prove the main statement, first let us concentrate on the case of simply connected ambient space. So it's, now I'm assuming N is simply connected. Okay. Because it was locally homogeneous, three-dimensional, and simply connected, and it's homogeneous, and then there is a list of such manifolds. And so it's good for my discussion to group in just two cases. First one is when n is isometric to a sphere times a real line with a standard metric, the sphere, any radius. And then the theorem holds because of it's contained. It's a particular case of the theorem 3 of Mix-Rosenberg that I showed you at the beginning of the talk, right? The second possibility is when the ambient manifold is isometric to a Lie group endowed with a less invariant metric. And that's the case I'm going to deal with, all right? Okay, so there are three cases for such a Lie group, a metric Lie group. The compact case, SU2, or the universal cover PSL tilde of the group of orientation preserving isometries of the hyperbolic plane, all right? Or a semi-direct product, which means what you see here in the blackboard, I hope you see it, is just, as a set, is just R3. But the structure of a Lie group is different from the standard one. So you pick a matrix 2 by 2, and then decompose elements in R3 in the horizontal part and vertical part, and then the structure of Lie group is cooked in this way, right? So you use the matrix, and then you exponentiate it and put the set coordinate there and do this computation. For instance, in the case of A matrix A being 0, then you find, of course, the standard R3. In the case of a multiple of the identity, you see H3, and these other choices give you an idea that there are lots of different ambient spaces, H2 cross R, Heisenberg, Sol3, the universal cover of the group of orientation preserving isometries of the plane, right? And any non-unimodular group is also contained in that, right? So there are a lot of such things. Okay. So we want to prove that the injectivity radius function, as I said, is bounded away from 0, right, in the intersection of a given end, annular end of the surface, with an extrinsic ball that I'm going to fix, right? So suppose not. Suppose that you can find points in the end which have injectivity radius smaller and smaller, and of course have to diverge intrinsically, right? So the goal of the idea of the proof is to blow up. But with some care, because you need a scale to blow up and to analyze the possible limits, but so that you don't lose the property that you see here. Or somehow this property is the only thing you have to work with, right? So usually, or there are a lot of scales you can use, but usually the simpler scale is by curvature. So you have something intrinsic happening in a surface or in a manifold, then what you do is you rescale so that the second fundamental form becomes, say, controlled, right? But also in reality, what happens in most of the cases is that then you can find something, of course, is non-flat, but is simply connected, right? In my situation, you will find a properly embedded minimal surface of bounded bounded curvature in R3, which is simply connected, so is the helicoid, because it's non-flat. So is the helicoid. So in particular, I lose the topology. So that's in a sense is kind of too fast. The scale I'm using is too fast. So I'm gonna to take a slower scale, and to understand that. You know that I like a lot Riemann minimal examples, so I'm going to explain that with the Riemann minimal examples, right? So the motivation is what blow-up scales are useful when you want to understand the local structure of an embedded minimal surface, right? The Riemann minimal examples come in a one-parameter family, are properly embedded in R3, genus 0, infinitely many planar ends, right? And come in a one-parameter family. In the two ends of this family, this one-parameter family, the modulus space, you see catenoids forming, a stack of catenoids, or two helicoids forming in the other stream. These two pictures are two Riemann minimal examples. And somehow, well, this one is pretty close to forming catenoids because you see here the neck, right? And what happens in the limit is that the any two consecutive planar ends become farther and farther apart, and then you see there a vertical catenoid forming, right, actually. And on the other extreme, the end of the moduli space, you more or less see this picture. Each Riemann minimal example is invariant under reflection symmetry in a vertical plane that here you see, say, just as a line, right? And on this part, you see like a helicoid which is forming, right? So you see actually two helicoids forming, one at each side of the mirror plane, which means that one is, say, turning, is left-handed, the other one is right-handed, right? Of course, in order to see a helicoid forming, then the other one has to disappear, right? Because both at the same time cannot exist, right? But what we are going to do is somehow to keep the distance between the helicoids, or the axes of the helicoid which are forming, fixed. I'm going to fix that distance, right? And that's the way we are going to normalize. This third picture, for me, is much more interesting because you see only the interesting part. It's helicoid forming, and then in between you have the symmetry plane that is not there. You have to imagine it. And everything else is pretty flat. It's very flat, very horizontal in the Riemann minimal examples, right? If you keep that distance between the axes fixed, then the limit, the limit of the moduli space, when you go to the helicoids, is a foliation of R3 by parallel planes. But that foliation has nice behavior along the two axes, because there the curvature in the sequence blows up. And if you rescale, then you see helicoids forming there. Okay? And then I'm going to call this picture on the bottom right, I'm going to call this a parking garage structure, right? With two columns. And the two columns are oppositely handed. Now you can understand everything, I think, no? Without any definition. So, okay. So that is the, well, what I'm going to show you now is a particular case of a more general theorem, rescaling by topology, or local picture theorem, scale of topology, also with Antonio Ross, that says what happens if you rescale by topology in a surface. Right? So I'm going to, I don't want you to pay attention to the delta function which is there because I'm not going to use it, so forget about that. Suppose that you have a complete embedded minimal surface, which lives in a homogeneously regular three-manifold. That means that, that you can find an epsilon so that the image through the exponential map of the ambient space at any point of the ball of radius epsilon is uniformly C2 close to a ball in Euclidean space, right? So suppose any compact, for instance, compact three-manifold is homogeneously regular. So it's a pretty weak assumption. And suppose that you have a complete embedded minimal surface and it has injectivity radius, so infimum of the function is 0, right? So you are in the situation we were. Also assume that it has locally finite genus. You don't need this assumption, but that produces a simplification of the theorem, right? That means that for every point in the surface there exists some radius so that the intrinsic ball of that radius, centered at the point, has finite genus, right? Then you can find points that I will call points of almost minimal injectivity radius so that, first, not only the injectivity radius at the points Pn go to 0, which is obvious, no, because of that, but they go to 0 pretty quickly. If you multiply by n, then they still go to 0, right? Now call epsilon n to this. Now, if I consider Mn to be the closure, that's the meaning of this, the closure of the component of the intersection of the surface with an extrinsic ball centered at Pn of radius epsilon n defined before, right, passing through the point Pn, that thing is a subsurface, is compact, and has boundary completely contained in the boundary of the extrinsic ball of that radius centered at Pn. Extrinsic, right? And this is, I'm not going to use that. This is where the delta function plays a role. But I'm not going to explain this because we will not use it. But somehow, well, the meaning of that is a chordate property, but forget about this, but I'm not going to use it. So it says that if you blow up your surface by this scale, so a scale on the inverse of the injectivity radius at Pn, right? Then for the rescale lambda n m surface, the injectivity radius, that's the meaning of I lambda n m, right, is bigger than or equal to 1 minus something small, so it's pretty close to 1, right, in Mn, in the rescaled Mn, of course, right? And also, if I use the same scaling for the ambient balls, then that converges to R3, right, with the standard metric. And how about the limit of the scalings of the surfaces? Well, you have two possibilities. Either the lambda n, the scaling of the blow-up of Mn, defined here, has uniformly bounded second fundamental form on compact subsets, or it doesn't. If it has, then the sequence converges after passing through a subsequence to a properly embedded minimal surface in R3 that passes through the origin, has injectivity radius 1 at the origin, because you have kept that property, and has injectivity radius function bigger than or equal to 1 everywhere. So it's not simply connected in particular. And the other possibility is the parking garage structure. The other possibility is that there exists some compact subset in R3 so that lambda Mn has not uniformly bounded second fundamental form, right? And then, after a rotation, it converges, the sequence converges to a foliation, like I said before. It's a parking garage structure with two columns, oppositely handed, like exactly the same like in the Riemann minimal examples, right? And also, you can find closed geodesics in the scaled surfaces that converge to a horizontal segment with multiplicity 2 that joins, is not written there because there's no space, that joins the two lines. So if I come back to the, to the picture there, is this. It's what I call a connection loop. Is you go there, then you go down, then you come here, and you go up. This is a connection loop that can be taken to be a geodesic in the surface, right? Okay, so let's go back to the proof of theorem 6. We had points where the injectivity radius went to 0. So I'm going to replace those points by points of almost minimal injectivity radius and call the same way, right? And then apply the theorem that I showed you. Then first case, when in the limit you see a properly embedded minimal surface, that surface has to have genus 0 because it's constructed as a blow-up of something which it was an annulus. Then by classification results, it's either a catenoid or a Riemann minimal example. Okay? The second possibility is just the parking garage. All right? So we have to rule out both situations because we are arguing by contradiction. The argument for ruling out both is more or less the same. I mean, I'm going to explain it in the case of a catenoid. In the other cases, it's just a modification of the same argument, right? Okay, so also you have a geodesic, no? The almost neck forming in the catenoid, right? And in particular, because when you rescale, you blow up, then the gamma n transform, lambda n, gamma n converge to the neck of the forming catenoid. Then in the original scale, the length of this gamma n goes to 0, right? That is going to be useful. Okay, so what we are going to do, I remind you that we had 3 possibilities for the ambient space: SU2, or PSL tilde, or a semi-direct product, right? SU2 is ruled out by this assertion, is that the points in the sequence diverge in the ambient space, which is impossible in a compact, any subsequent diverges, right? It's impossible in a compact setting. Okay, so the proof is more or less the following one. suppose that you have convergence of the points Pn to some point in the ambient manifold, right? Then take normal coordinates for the ambient manifold around this limit point, so that when you rescale by the topology, as I explained before, then the coordinates you find in R3 are so that the limit catenoid is placed vertically. So it has vertical flux, is what I'm saying, right? Has vertical flux. Now, define a Killing vector field on your Lie group, which is a right invariant vector field given by the value at p infinity 001. That if you right translate that value, then you find a right invariant vector field. So that defines a Killing field. And then the tangent part is Killing on the surface, and you can find an homology invariant defined as the flux, the scalar flux associated to this vector field, which is just the integral of the tangent part of V times the unit normal vector integrated along any closed, say, cycle, and that is a homology invariant. What's the contradiction that rules out this case? If you rescale the flux, of course, it converges to the scalar flux of the limit. That is because of the choice here is 1. So in particular, it's non-zero. The only thing you are going to need is non-zero. That means that this factor here cannot be 0 for n large. But if it is not 0, since it's a homology invariant and the gamma n can be taken to be embedded curve, then it will be homologous to the boundary. So actually that number has to be fixed along the sequence. But you can use Schwarz inequality in order to know that that number in length goes to 0. Just think of the value of V at the point P infinity is 1. So in a neighborhood, a small neighborhood, is pretty close to 1. So in particular, it's bounded. And the curve, say, the neck is very tiny and passing through Pn, which is converging to P infinity. So you have this C here bounded the length of the vector field. Okay, so that's a contradiction that shows. 10 minutes, no, more or less. That shows that SU2 cannot happen. So I'm going to show you now a sketch of the idea that rules out PSL tilde, right? And more or less the same idea also rules out the similar product. You need to change. I'm going to use a foliation, and then you need to change the foliation in the other case, but the argument is the same. Here, the fundamental tool is what is called the left invariant Gauss map. What is that? You have a surface. Well, here I have used E, the end, but in general, you have a surface. And you have the surface is two-sided, so you have a unit normal vector at each point. And this is nu here, nu at P. Then left translate that vector to the origin. Right? Left translation is an isometry because I'm using a left invariant metric. That produces a vector at the origin which is unitary. So that defines a map from E into the unit sphere in the tangent space at the origin of the ambient space. That's the left invariant Gauss maps. Now, take points Qn in your end, which are close to the, say, centers of the rescaling, so that the values of the Gauss map at them converge to the normal at one of the ends to the forming catenoid. And then consider the values of G at Qn. Then this is a sequence of points in the sphere. It's compact, so after passing to a subsequence, converges to some W value there. Okay. Now I need to remind you something about two-dimensional subgroups of PSL tilde. Here you have a picture that you can understand. This is the hyperbolic plane, and I pick a point theta in the ideal boundary, and I consider the orientation preserving isometries that fix that point. All right. This is a two-dimensional subgroup of PSL to R, and then this two-dimensional subgroup you lift to the universal cover, passing through the identity, and then you create this way a two-dimensional subgroup of n. N is the ambient space I'm dealing with, right? And these are all two-dimensional subgroups in my ambient space, right? Of course, every two-dimensional subgroup has constant left invariant Gauss map. It plays the role of a plane in geometry of R3, right? And for each zeta, if you move a zeta in that picture there in the blackboard, then that value, constant value of the left invariant Gauss map, identifies the subgroup. So that defines a closed curve, which is a one-to-one in the sphere. All right? Now pick a value of zeta, called zeta naught, so that the corresponding g is not plus or minus the w that I found above, right? And now consider the following thing. It's better to go to the picture. Okay, here you see the picture. H tilde is the subgroup that I defined a minute ago. And P1 H tilde is just an image through an isometry. It's a left translation. So you take the left class that passes through P1, isometric to H tilde. That's a kind of a plane. And then you see there, consider a tubular neighborhood of that plane, say, that subgroup, which is not a subgroup, but of the radius epsilon 1. And take epsilon 1 so that gamma 1, I don't see it very well, but is completely contained in that neighborhood, and also in the ball of radius epsilon 1 centered at P1. And do it for any k, not only for P1. And because of the construction, you can take the epsilon k's smaller and smaller, right, going to 0. Okay. Now, if I write, look at here, if I write P1H as H1 P1, where H1 is just a conjugate of H, all right, I have written this left class as the right coset, right? And now I'm going to fix this H1, which is another subgroup, and I'm going to consider the set of right cosets associated to it. And you can show that is a foliation of the ambient space by equidistant surfaces, right? So in particular, this one, the boundary, and this other boundary component, and this also, well, this, okay, these two boundary components, sorry, these two, are two leaves of this foliation, okay? Now, think of gamma k. Gamma k is contained in a very tiny ball there. So in particular, gamma k cannot intersect both boundary components, say delta 1 and delta 2 of this neighborhood here. No, because they are separated by distance epsilon 1, or 2 epsilon 1. But epsilon k is much smaller if k is large enough, right? So gamma k cannot intersect both. So suppose that means, sorry, if it doesn't intersect both, that means that gamma k has to be on the same side as gamma 1 with respect to the complement of gamma of delta 1 with one of the boundary components, or of gamma of delta 2. Let me say it again. Think of delta 2. This curve gamma 1 is on the, say, bottom side of delta 2, but gamma k is on the top side of delta 2. So delta 2 is useless. But delta 1. Gamma 1 is on the same side, is the top side with respect to delta 1 as gamma k, which is also on the top side. That means that if now I consider A1, gamma 1, gamma k to be the annulus inside E, bounded by gamma 1 and gamma k, then the boundary of that annulus, right, is on one side of this plane here, this delta 1. Right? But I can take, because of the shape of the catenoid, I can take the catenoid so that, or not the catenoid, I mean the situation so that the boundary components of the catenoid intersect both boundary components of this one and this one, right? So in particular, you can consider now the restricted foliation of this half space at the bottom of delta 1, and find a right class in this foliation which is furthermost with respect to the annulus, right? And that furthermost leaf will intersect the annulus with boundary, right? But not at the boundary, at the interior, right? And that's a contradiction with the maximum principle. Why? Because that intersection, I mean, what I have drawn here as a line is actually a right coset, and a right coset is isometric to a left coset, which is isometric to a subgroup. And in a unimodular group, every subgroup is minimal, right? So both surfaces are minimal, so that's a contradiction, okay? For the general case, that finishes the proof of the simply connected case in the ambient space. For the general case, I'm only going to say a couple of words because I have 1 minute. Okay, the idea is as follows. Well, first, you do the same thing by contradiction. Suppose that the injectivity radius function is not bounded away from 0, right? That allows you to find the sequence Pn with a smaller and smaller injectivity radius, and then replace those points by points of almost minimal injectivity radius, apply the theorem, and as before, you find two possible limits, catenoid or Riemann minimal example. One possibility, the other one is the parking garage structure, right? Also, as before, you can find a geodesic connection loop with smaller and smaller length in the original scale, all right? And now you discuss on if that connection loop is trivial or not in pi1, in the fundamental group of the n. Yeah? If it's not trivial in a subsequence, if it is not trivial, that means, with a little thought, that you can lift your end, your embedding, which was in n ambient space, to the universal cover of that n. And then you can apply the previous case, because you have the same situation upstairs, right? So that's impossible. So the other possibility is that the connection loop is trivial in homology, in the annulus, right? If this happens, then the contradiction comes again by flux, because if this happens, the flux of the surface associated to any vector field you want, any Killing field, right, has to be 0 because you are computing it in a curve which is 0 in homotopy, right? And well, bounds a disk, so it has to have a 0 flux. But when you rescale, then every limit you find, catenated Riemann minimal example or minimal parking garage, have associated a non-zero flux. For the catenated and Riemann minimal example is trivial. For the parking garage, it's not so trivial. The way to understand that is that, as I said when I showed you the local picture theorem and the scale of topology, the connection loop converges to a curve that, to a segment, right, which is covered twice. And the segment joins the two columns of the parking garage. If you follow, you keep track of the conormal along the sequence to the surfaces in the sequence, then you see that the conormal converges to horizontal, the same values. And then you go, if this is a connection loop, then you go like that. This is a conormal, right, that goes through the picture would be like that. That's the columns, and here is the connection loop, right, goes like this. And then if I use some perspective, it's like this. That's the conormal. In particular, the flux of this, if you compute the integral along that connection loop, in the limit, the flux is twice the length of the distance between the two columns, which is non-zero. So again, that is the same contradiction as before. You have non-zero flux, but it was 0 flux in the sequence. So that's the idea, and that's the end of my talk. So thank you for your attention.